I think we're all good to go. So, hey everybody, my name is Sean Hurley. I am a staff engineer at Coinbase, where I work on our data source team, and I want to take a little bit of time today to talk about some work that we did with the Atlas team in rapid autoscaling with MongoDB.
Hi, I'm Matteo Vesperini-Heydrich. I am a lead engineer on the Atlas dedicated team, and I'm hoping to share a little bit more about what we did behind the scenes to help with this Coinbase initiative.
Oh, do we have a clicker?
Oh, yeah,
there we go.
There it is.
Thank you. Cool, so for a little bit of background, like I said, I work at Coinbase. We're a crypto company. We have a lot of various products and features that do different stuff with crypto, whether that's the pretty simple buying and selling Ethereum as sort of an investment, maybe using it to pay a merchant or accepting payments as a merchant, staking, any sort of on-chain tools are things that we try to provide. And for some more specific background on what we're going to be talking about here, we have hundreds of Mongo clusters that power various different experiences. Each of those experiences have vastly different resource requirements. Some of them are going to be really, really write-heavy and need more IOPS. Some are going to be really read-heavy and maybe need more RAM. And we often kind of get asked this question of, hey, Sean, how many requests can MongoDB handle? To which I always respond, well, which Mongo cluster are you talking about? And they're like, no, just kind of in the abstract, how many requests per second can MongoDB handle? And that's sort of emblematic of this pattern where, for the most part, product engineers don't really want to think about their database. They want to provision a cluster, and they want to write some data, and they want to read some data. They don't want to think about CPU or IOPS or RAM or anything else. They want their data to work. And so they lean on our team to build them the tools to make that as automatic as possible. And where it gets really, really challenging is that the traffic in the crypto space is extremely volatile and way less predictable than traditional fintech. I've worked at other fintech companies and at places like Venmo. You could generally plan on the beginning or end of the month being a lot busier as people split their rent bills, or the Super Bowl being busy as people split bills. At Uber, people would always take a lot more Ubers on New Year's Eve, so you could plan on that. But in crypto, it's way, way less predictable. And I think my favorite example of this is things like this, where Elon Musk changes the Twitter icon to a Shiba Inu, and all of a sudden everyone wants to buy Dogecoin because it is the coolest next thing. And the end result is that our systems suddenly see a massive spike in traffic that we had no heads up for. Elon doesn't send us a text in advance of this, he just does it, and then we find out later on when all of a sudden our databases are overloaded. So that's really what we wanted to try to figure out how to handle here is, how do we handle these weird, unexpected traffic spikes? And where we started was something kind of like this. We'd be provisioned for some level of traffic, and eventually, when traffic got to that point, we would have to start upscaling. And what's kind of shown in here is these sort of like dotted lines under the curve. Those are user requests coming in beyond what we were actually provisioned for. So these were things that we essentially had to drop, or they would be really, really slow. It was a really bad user experience. And eventually, the database scale-up would finish, and traffic would start rising up again as the site came back online, and then we'd have to scale up again. And we'd kind of constantly play this game of having to wait for our database to be ready for user traffic rather than being prepared in advance. So the first thing we had to do, like I said, we have a couple hundred Mongo clusters. We need to figure out which ones of them need to be scaled up and how do they need to be scaled up. So we looked at a couple different things. First off, let's identify the clusters that correlate with actual user end traffic. Let's figure out what resources do they need. Is it more CPU or IOPS? And really, really importantly, how much do they need so that we can pick the right capacity and not have to play this game where we're constantly scaling up a little bit more, and kind of guessing and checking. And the way we sort of tackled this was by modeling it based on previous traffic spikes. So what we would do is we would essentially correlate a various resource like CPU or IOPS against end user traffic, so user activity on our site, and try to figure out how does that actually correlate with resource utilization on the database. We could then take that correlation, look at the sort of slope of the line to say, oh, well, as user traffic increased, here's how much CPU increased on this specific cluster. And we could then extrapolate into the future that if user traffic were to continue to increase, here's how much CPU we would need in the future. And what that kind of looked like in practice is something like this, where there would be some clusters that really showed no correlation at all. And what we have here on this chart is, on the x-axis is user traffic increasing, and on the y-axis in red, we have CPU, and blue, we have IOPS. And in this particular case, there's really not a clear correlation between user traffic increasing and either resource utilization increasing. So we can kind of look at this and see like, well, this particular cluster is not really correlated with user traffic. Maybe it serves some internal tool, but something that we don't necessarily need to scale up and down as traffic spikes occur. On the flip side, we have some really critical clusters that serve like core user or account data that has very, very clear correlation that as user traffic increases, both CPU and IOPS grow with it pretty directly. And so here, it becomes pretty obvious that we can sort of look at the slope of that line and extrapolate into the future that if traffic were to continue to increase and say double again, how much CPU would we need to provision in advance to be ready for that? Yeah. Yeah, so the question is basically like, how did we actually fit this slope? Like, why did we just use linear as opposed to basically anything more complicated? And the answer is that for the most part, linear has worked pretty well for us, and the times that we've seen it be more quadratic, it tends to be when things start to tip over anyway. Like when you start to see CPU go from 5, 10 to 90, that's generally like there's been something more fundamentally wrong, and so we haven't really wanted to capture that signal in the first place. But to your point, there are way more complicated ways that we could model this in the future for sure. Yeah. Yep, and we'll talk about that a little bit more in a second about vertical versus horizontal. So we've got these capacity planning models. Let's talk about autoscaling, and thank you for the segue. Why aren't I talking about horizontal scaling? And the sort of key aspect of this is that we're talking about very dynamic scaling. We're talking about dealing with day-to-day or hour-to-hour traffic spikes. And in this case, we can't really talk about sharding. You cannot add and remove shards on a whim. That's a really, really slow process. So we can kind of rule that out. So really, when we talk about dynamic horizontal autoscaling, we're really talking about adding and removing read-onlys. And in this case, first off, that's only going to help read traffic. So like that doesn't help too much in some use cases. But then the process for adding a new read-only node and scaling horizontally requires this sort of process of, okay, well, first off, we spin up a new instance. We then copy the EBS snapshot, because we're all on AWS and EBS volumes. We then have to replay the op log to catch up that node to the latest data. And then we have to do this really annoying step where we have to tell AWS to like pre-warm the data to actually sync everything in real time rather than lazily fetch the data. And then after all that's done, we can start serving traffic. And from some of the benchmarks we've run, that process can take like an hour for just a half a terabyte. And so when we're talking about dealing with Elon Musk's random shenanigans on the internet, that's way too slow. We need to go much, much faster. Which is why we were really focused on vertical scaling here. The process is a lot more straightforward, where a node announces like, hey, I'm going to go offline for a second. And then one really important detail is while that node is offline, the other nodes in the clusters kind of have to pick up the slack and handle any traffic that that node would have, which can result in some performance degradation that we'll dig into. While that node is offline, its instance type is resized, and then it joins back on. And all around, this is quite a bit faster of a process. But to dig into that second point, because that's really important, I'm talking about auto-scaling with traffic spikes. If we're scaling up while we're under load, what does that mean for the user experience? Is the cluster still going to perform well? And so we looked at some various benchmarks to try to isolate a few different variables. So first off, we wanted to look at very, very small instances versus kind of medium or large instances. It turns out that in AWS, if you are doing an instance resize for pretty tiny instances, it's actually quite a bit faster than it would be for medium to large instances. But really importantly, what we cared about was, well, what happens if we scale up when CPU is only at 50% utilization, or what if we wait until it's at 80%? And we see some pretty drastic differences, and sort of as you would expect, because while a node is offline, the other nodes in the cluster have to pick up the slack. At 80% utilization, you see some drastic performance degradation where read and write latencies can increase 50, almost 70%. And for fintech, where you're pretty latency sensitive a lot of the time, for all intents and purposes, you're down here. Users just can't use the app at this point. So what we can kind of take away from this is that we need to scale up as soon as possible. We cannot wait until the clusters are already starting to get overloaded. We need to do it ideally before traffic even gets here. And so the way we tackled that was by working on trying to build an ML traffic prediction model. And this could be a talk in its own right, but to sort of like summarize it at a high level, what we've done is we've looked at prices of various cryptocurrencies and specifically the volatility of those prices. And we've used that to train a model that can predict when traffic is going to happen. So while it can't necessarily predict when Elon is going to change Twitter's logo to a Shiba Inu, it can see that initially there is some volatility as people start to trade, and it can trigger pretty quickly and much more rapidly than any human would be able to catch that and start to scale up. And so what this kind of looks like in practice is that in this graph, this was one of the traffic spikes we saw, where red is when the model kicks in and says, like, hey, we're seeing some volatility kick in. We think we need to be prepared for some like big traffic spikes. And green is when the databases were actually able to finish scaling up. And so in this case, we were able to be scaled up well in advance of the actual big main traffic spike. So our databases were already ready to go, and users didn't have any negative experience. Right now, the model is only trained on price data and price volatility data. I think there's absolutely a lot of room, and our ML teams are looking at, yeah, can we feed in, Twitter mentions or any other social media things or news postings? There's a lot of different signals that could get fed into this, but for now, we've actually found that the price time series data has been pretty good. Oh, cool. There's a soft. Well, I certainly can't speak to if the SEC would do anything about that. I will say there's an interesting thing here, and while I'm talking, if someone can cancel the software update, that'd be cool. But while this is able to predict the sort of like volatility and the traffic spikes we're going to see, it hasn't really been able to track whether or not the price is going to go up or if it's going to go down. So it becomes really hard to trade on if you don't know which way things are going to go. But I think you're absolutely onto something that if like you could build this perfect model that could predict price, but rather than Coinbase traffic, it'd be something you could trade on. But for now, that's not something that we've been pursuing. Cool. So the next thing that we really wanted to focus on was keeping the gap between that red line when the model alerts that we need to scale up and the green line when the scale up finishes. We want to keep that as narrow as possible, because in this case, there was a nice time delay between when the model triggered and when the traffic got here. That might not always be the case. So we wanted to figure out like how much lead time does the model need to give us. So we started looking at how long does it take to scale up clusters. And again, trying to isolate some variables, first of which, again, looking at instance types, and also looking at how many nodes are in a cluster. A lot of our clusters are going to be small 3 nodes with just the 2 electable or 3 electables. Some of them are going to have a couple of read-onlys, and some of them are going to have read-onlys and analytics. And what we started to see is that, as you'd expect, the small clusters scale up really quickly, like 15 minutes. That's really not a big deal. That's great. But our biggest clusters, which are also our most important ones that have a lot of read-onlys and a lot of analytics, we're taking over an hour, which is really painful when we see those big traffic spikes to then have to wait a full hour to mitigate incidents. So we decided to see, like, hey, Atlas, what can you do to improve this? And as sort of a sneak peek to what Matteo is going to be talking about, we were able to make some massive improvements where things that used to take 23 minutes now take 14. And more importantly, those huge clusters that are really critical to Coinbase's infrastructure now, rather than taking over an hour, only take something like 24 minutes. So as long as our model can give us about a half hour's heads up, we can have all of our clusters scaled up, ready to go and serve user traffic well before the traffic even actually gets there. So Matteo, do you want to talk about how you guys were able to do this?
Yes, of course. Thanks, Sean. It's super interesting to hear about how you improve forecasting to make this easier. So I want to talk a little bit about the partnership with Coinbase. I'll talk about how we approached it. We'll go into some of the technical details of what we improved, and then I'll talk about a little bit for what's next for cluster scaling. So first of all, when we heard that we were going to work with Coinbase, my team was super excited. It was a good opportunity to get into real-world use cases and look at real clusters and see how those scaling plans were proceeding. And we knew that any work we did here would apply to a lot of the other Atlas customers. And the goals were clear. We really wanted to speed up vertical scaling in particular. And as a second order goal, we wanted to make sure that crypto volatility events were a non-event for Coinbase customers. So we delivered this in 2 phases. The first phase, we wanted to provide relief to Coinbase as quickly as possible. We shipped this in around 30 days after we had the initial discussions and you outlined the problems that you were seeing. And then we had a second phase that I'll talk about after this. The first phase was more straightforward ideas, things that were low risk, and we just wanted to get Coinbase in a better place as soon as possible. So let's talk about some of the improvements. This is a cluster scaling plan before any of the changes that we made. And you can see this is a typical 3-node replica set. There are 2 secondary nodes on top and then a primary node on the bottom. And for each node, what we do is we go through a series of steps before we move on to the next one. The first step is upscaling compute. So we turn off the machine, we increase the amount of CPU and just CPU that it has available. And then next we turn back on the database processes and we make sure they're running correctly and smoothly. And then in some cases, you'll also have networking health checks that happen, typically with a load balancer, before we proceed. And then finally, we'll upscale the storage. And this is done for every node. So the first thing that we found is that sorry, go ahead. Yeah, so I don't know if we want to share any particular cluster sizes, but these are going from like very high-end clusters to even higher-end clusters for the most core cases. But this is true for.
Yeah, is my mic still on? Yeah, we use secondaries very, very heavily across Coinbase, so we have read-only nodes on a lot of the clusters.
Cool. So first thing we found, the load balancer health checks, we didn't really need them. We had already checked that the database was available and functioning properly, so these were just duplicate to what we had already been doing. We were able to reduce the time that they took and parallelize them with the other health checks that we did. This immediately saved about 3 minutes per node. Beyond that, we dug into the other health checks that we did, and we realized that we had introduced an artificial 1-minute wait on those health checks for very niche networking situations. So we were able to remove that and then also save another 30 seconds per node. And then finally, we made sure that in all cases we were doing storage upscaling before any of the other compute upscaling. And the reason for this is that these updates are very fast. They take about a minute per node. And if a cluster is I/O bound, this can immediately improve performance by increasing IOPS. So we do that first, and then we proceed to the compute upscaling. And the results from this were huge. So already, Sean had given you a little bit of a spoiler, but we took over 30 minutes off one of the most core and largest clusters that Coinbase has, and we saw somewhere between a 1.4 and 1.7x improvement overall in cluster scaling speeds. And those were only some of the improvements that we made in phase 1. But we knew that we could do better. So phase 2, this was delivered in about 90 days after the initial conversations with Coinbase, and it was centered around this big idea of parallel scaling. So this is how scaling used to work. And we would always go node by node. This is a 6-node cluster, and you can see that it has 3 electable nodes, 1 read-only node, 2 analytics nodes. This is similar to Coinbase's setup. They typically have all 3 node types. But in the case of a big traffic spike, the most important thing is to get to the next tier as quickly as possible. So we introduced new scaling modes. This is the most aggressive one, which is node-type parallelism. And it allows you to scale electable nodes, read-only nodes, and analytics nodes at the same time. The results from this were even bigger than before. We were able to take over an hour off of some of the most important scaling plans for the 7-node cluster shown here, and just generally, it was much faster than before, somewhere between 1.8 and 3x improvement. So what were the results? Vertical database scaling is much faster and also more predictable. There's some predictability improvements I didn't really talk about. Coinbase can now handle crypto volatility without any issues. Customers can continue to trade in all cases. And we've also benefited other Atlas customers because of the improvements that we've shipped. First to Coinbase and then to the rest of the fleet in this case. So where are we going next? Well, first of all, phase 1 has been live for a few months. So if you've had similar configurations, you've already been benefiting from the improvements that we shipped here. Second of all, parallel scaling is available as of last week. You can find it in the API, and you can also find it in the cluster builder UI. And you can choose between different scaling types for whatever is most appropriate for your cluster. Beyond that, my team continues to work on cluster scaling improvements. There are already projects underway to continue to make these kinds of gains. And one thing that we're focusing on is predictability. So we know that if you can usually scale a cluster in 20 minutes, that doesn't matter if it takes 2 hours when it's under load and you need to get to the next tier immediately. So that's a major focus. And generally, we're just making speed improvements. If you have any unique scenarios that you want to work through with us, please just contact your account team or Atlas support. We thought that this partnership was very effective, so we'd be interested in taking up others if there are unique situations. No. You mean MongoDB version, right? Yeah. Yeah, no, you don't. Yeah. And then I just wanted to give a quick shout out to the engineers that actually made this happen. Brad, Dimitri, Jeffrey, Ming, they're all MongoDB engineers that actually implemented these improvements. So let's give a hand to them really quick.
Yeah, so we have a number of sharded clusters, and they still benefit from all of these changes as well. They actually benefit quite a bit more because, for the most part, our sharded clusters tend to run on much smaller node types, just with more shards. And so they're able to scale up way faster because there are those smaller instance types, and it's pretty quick to do that. Sharding also helps quite a bit because all of the shards can be scaled up in parallel already, very similar to what you were talking through with the node type parallelism. It's already parallel across shards. So yeah, we have a number of sharded clusters. They already benefit pretty heavily, but the key here was focusing on some really old legacy ones that we haven't had the time to shard yet.
And for sharded clusters, I don't have a diagram of it, but the parallelism applies to each shard in the cluster. So the shards were already parallel, and then within each shard now you can do this as well. No, not yet, no.
Not yet, huh?
So if you only have electable nodes, you're saying? Yeah, so if you only have electable nodes, this won't benefit you. That's true, yeah. Yes, there are other improvements. Even in phase 2, we shipped other smaller improvements, like making sure that, well, I guess this wouldn't benefit you, but when you have an unhealthy analytics node, we won't block on that anymore during upscaling plans. So there are other improvements that you will benefit from, yes, definitely, especially part 1.
Two questions. Scaling down is the opposite, just another API call.
Yeah. So I believe we did not parallelize downscaling because it wasn't as much of a priority, but I'll check on that because if we didn't, it would be easy to implement. Oh, sorry, the question was, does this apply when downscaling? And is it the same API call? And yes, you can edit your cluster and go up or down.
And then the second question was, obviously you're bringing your own signal to do the scaling, like if you're offering Atlas as a managed service, what signals does it act on itself?
Right, so I'm not the autoscaling expert, but we do look at CPU and memory usage to determine when to autoscale a cluster, which is an option that you can enable. The question was, Coinbase has inputs that they provide themselves and they manage their own scaling. What do we offer? And the answer is just, it's based on CPU and memory and possibly some other metrics. Yes, so if you enable parallel scaling, for example, that will happen during your autoscaling plan as well. And the phase 1 improvements are also baked into any autoscaling that happens, yeah. So the question was, would this apply to read and write heavy databases, or is it different between the two? So, I mean, the parallel scaling will still happen in either case. I think with read heavy workloads, you need to be a bit more careful about selecting the maximum parallel scaling because then that can bring more read-only or more read-capable nodes offline at the same time. So it may not be you may not want to enable node type scaling, and you can work with the account team to figure that out. But for write-heavy databases, almost in most cases, you should be able to enable the maximum scaling. Yeah.
My experience with autoscaling is that it's pretty hard, and I was wondering if you have a
Is this this is a Coinbase question, right?
I assume so, because you're looking for the signal to upscale to the next tier, right?
Yeah.
Yeah.
So you guys, I'll let you explain. your
Yeah,
system.
so, and this is where it became kind of interesting because we're not doing autoscaling in sort of a traditional sense by looking at metrics of the cluster itself, because we don't want to wait until the cluster is already using those resources to try to add more. And so, yeah, we had to work with another team to try to figure out, like, hey, we have this problem where we can't wait until the cluster is under load to trigger a scale up. Like, what other signals can we find? And that's where we landed on using the currency price data, because that is a pretty good indicator of user traffic on our site. And so we can then kind of use that to forecast into the future when we need to actually do an upscale. Yeah, so the question is 20 minutes good enough? And for the most part, from what we've seen, yes, it has been, assuming that the model is able to trigger in time. Like this slide right here, it was able to trigger well beyond 20 minutes. It was, I think, more like an hour in advance. So for most of what we've seen in the past, that heads up has been good enough. But that's not to say that tomorrow we couldn't see a brand new traffic pattern that goes off in 5 minutes. But so far, it's been good enough.
Was there another?
Scale down happens after 24 hours after the scale up event, right?
Yeah.
Is there a roadmap to customize that based on user needs or predictive?
I don't think I can comment on the roadmap, but there are a lot of improvements in the works. The question was, can we introduce the ability to customize how autoscaling is triggered, especially for downscaling? And so I will say there is a large focus on scaling in general, including autoscaling. So I hear the feedback, and yeah, there are things in the works for sure.
Is there anything in the works to make the horizontal autoscaling a bit faster?
Right. So the question is there anything in the works to make horizontal autoscaling faster? It's definitely a pain point that we're aware of. There are some fundamental limitations on how we can do that with the current architecture, because the data has to be copied to a new node. It's something that we considered when we were brainstorming ideas for these two phases of improvements, just in case there was something to do there. I think the answer is not in the short term.
As one example, because this is something that we don't feel this pain just on Mongo. This applies to all of our databases. The one exception would be something like Aurora, where compute and storage are separated. That makes it a little bit easier to follow this sort of paradigm, but that's like a massive re-architecture of how the database works to be able to get those benefits. Any other questions? Yeah.
So how did you guys negotiate like the trade-off between, I guess, like the reliability of your existing clusters with the optimization of, I guess, auto-scaling? Because you mentioned that you had removed a couple checks earlier, and so I was wondering like if that may have like been a discussion that you guys had, like the trade-off between like the efficiency, or sorry, resilience versus efficiency.
I think the first thing so the question was, when removing, generally, was there a trade-off between efficiency and resiliency, especially when removing these kinds of health checks or reducing the health check time? The answer is the changes that we made here are essentially completely safe. We tested them under load extensively. We don't think that they were valuable or helping ensure that clusters are safe. We haven't seen any regressions as we rolled it out to the entire Alice fleet, which we do gradual rollouts for. So I don't think there will ever be any issues that arise from these changes. For example, this one was only applied in a very niche networking situation that involved VPC peering and split horizon DNS. So it's still in place for that rare situation, but we've removed it for other clusters which never needed it in the first place. There was no reason to introduce it for other clusters.
Okay, I think we have time for one more question.
How many tiers are you normally scaling up by? Like, is that ML model predicting just go up by one? Because you mentioned already pretty high tiers in the first place, or is it giving you input as like, you should go up 2 or 3 tiers?
So the model itself, the question is basically, how many tiers are we going up by? And The ML prediction model is predicting what the traffic level is going to be. So it's going to say, hey, Coinbase.com is going to go from currently, I can't use specific numbers, but say, to 10 requests a second to 20 requests per second. And our capacity planning model is what actually translates the end user requests into resources required on the cluster. So in practice, it varies wildly on the cluster. For some of them that have really strong correlation, like user cluster that gets hit every time on every page load almost, that is oftentimes going to go up by several tiers at once, whereas some smaller clusters might only go up one tier or even just a half tier, something like that. So yeah, it's kind of a combination of predicting what traffic will be and then translating that to, for each cluster, how much CPU and how much RAM does it need.
Awesome. Thanks, Sean and Matteo. We are at time. That was awesome.
Thanks.
Appreciate that.
Yeah.